Okay, welcome back to our videos on radioactivity. We're going to talk a little bit about carbon-14, how does it work and how do we use it, and then mention some other uses of radioactive sources. In terms of carbon dating then, how is carbon-14 formed? You're not really needed to know this for the AQA spec, but it's nice to know. It's formed by cosmic rays knocking out neutrons in the upper atmosphere from other atoms. These neutrons then go on to collide with nitrogen. Most or 80% of our atmosphere is nitrogen. You should have known in previous studies at school, and this creates carbon-14 in the following reaction. So you've got a neutron colliding with nitrogen-14, causing carbon-14 and a proton to come out. This carbon-14 is unstable, so it decays via beta decay back to nitrogen-14, and here's the beta negative particle and the antineutrino. So you've got a constant creation and decay of carbon-14 in the atmosphere, and this maintains a relatively constant amount of it. Now, when things are alive, they're constantly exchanging carbon with the atmosphere, so as long as they're alive, a constant proportion of radioactive carbon is kept in their bodies, and this is in comparison to the other types of carbon. But unfortunately, when the particular organism dies, this exchange stops, so the amount of carbon-14 begins to decay. The other types of carbon remain constant, but the radioactive carbon will decay, and what we can use is this amount of radioactive carbon left can be used to work out the age of the sample. And when we say age, we don't mean how old it was when it died, we mean how long ago it died. So a very straightforward question. A sample of wood from an archaeological site was burnt and the carbon dioxide produced was collected. The activity of the carbon dioxide was equivalent to 5.4 counts per minute per gram of carbon after background correction. Same mass of sample wood from a modern living source had a corrected count rate of 18 counts per minute. So the one that's alive should have 18 counts per minute. The one that's died is going to just decount to 5.4 counts per minute. How old is the find? We know we're given the half-life of carbon-14 of 5,750 years. So using our two equations, that lambda equals log 2 over the half-life, and activity is the original activity, e to the minus lambda t. First of all, we can work out lambda. So if we work out lambda for carbon, log 2 over 5750, this is 1.21 times 10 to the minus 4 per year. So this is the chance of decay is that amount per year. Then we can feed this number into our standard exponential decay. So our activity will equal the original activity, so our 5.4 given in the question counts per minute is equal to the original 18 counts per minute, multiplied by e to the minus lambda, just calculated with t, and we're trying to work out what t is. Just a quick aside, the 5.4 and 18 have both got the same units, and these are in counts per minute. And then we've left our 1.21 times 10 to the minus 4. This is in per year. So the answer that we get, t, is going to be per year, because these two expressions, lambda and t, must have the same units, and our a and a0 must have the same units. Okay, so if we just do natural logs of both sides, then we get natural log of e, which cancels out. We can do a little bit more maths, so log 5.4 over 18 gives minus 1.204. Then we can divide 1.204 by minus 1.21, and this gives us a value of t of 9,950 years. So using a count from a sample of wood, we have managed to work out its how long ago it has been dead, and it's nearly 10,000 years. Some other quick uses, again mentioned on the spec, just an appreciation of these uses: phosphorus 32, medical tracers, it's got a half-life of 14.2 days, iodine, medical tracers 8 days. You can see you need a very short half-life for anything to do with medical tracers. Strontium often used as power sources, so a longer half-life. It's going to be good to power something for at least 30 years. Potassium 40, half-life of 1.25 billion years, so we use that for dating of rocks. Carbon-14, anything that's been alive. Sodium-24 can be medical tracers, underground pipes, leaky pipes putting into maybe water sources, etc. So a low half-life. And the humble smoke alarm, Americium-241 uses an alpha source. So again, in your background reading, just have an appreciation of the different uses of different radioactive isotopes.